Okay, so let's have the second part of the applications of first order differential equations. So we'll be discussing two applications here, the growth and decay problems, and Newton's law of cooling and heating. The rate at which the amount of a substance changes is always proportional to the present amount of the substance. And if x denotes the amount of the substance at any time t, then the rate of change will be represented by dx over dt. If k is the proportionality constant, then your dx over dt, so using the proportionality constant, no? So directly proportional to k, rather to x. So this should not be included. And then translating that to equation, then you have to introduce a constant of proportionality. The population of a city doubles in 50 years. So in how many years will it be 4 times as much? Assume that the rate of change is proportional to the number of inhabitants. So let x denotes the population of the city, and then it says that the rate of change is proportional to the number of inhabitants. So the differential equation is dx over dt equals kx. So we're not given the initial condition, let it be x sub o. So initial condition, that is when the time is equal to 0. And then what is the time when the population is 4 times the initial population? So x is equal to 4 times the initial condition, the initial population. Then if you have dx over dt, so cross multiply here, so dx over x, so integrate, and then what is left in the right hand side is k dt, so integrate. We have ln of x equals kt plus c. Okay, solving, if you have ln of x here, solving for x, that will give you e to the kt, no, plus c, or e to the c. You can split the power, but since c is arbitrary constant, so you can represent this also by an arbitrary constant. So that will be your general solution. And then at the initial condition, your c is always equal to the initial condition, no? So just substitute here, so e to the 0, and then x is the initial condition, x sub o. And then at, so using one condition, that after 50 years the population is doubled. Okay, so substitute in the general solution, taking c equals x sub o. So this is your x. Okay, this is your x, and then this is your c, e to the kt, so that the time is 50. So this will cancel out, and then taking the ln of both sides, now we get ln of 2 here, and then ln of e to the 50k, but ln of 50k, so that is the same as 50k times ln of e, and ln of e is equal to 1, or k is equal to ln of 2 over 50, or that is equivalent to 0.01386. And then solving x as a function of time, So x, okay, so x is equal to x sub o, the initial condition, e to the ln of 2 times over 50 times t. So at any time t, you can compute for x, no, in terms of the initial condition. So if this is given, then you will have a numerical value here. Or given time, you can solve for the population. So we're asked for the time when the population is 4 times the original. So this will cancel out. Okay. And then you have ln of 4. Take the ln of both sides. Okay, so actually you have ln of e here, but ln of e is 1. Okay. And then solving for t, that gives you 100 years. Okay, let's have another example. So 30% of radioactive substance disappears in 15 years. So find the half-life of the substance. Okay, what is half-life? That is the time at which the amount of the substance is 1/2 of the original amount, no? Or equivalently, your x is always represented by 0.5 times the initial amount or original amount. So if x denotes the amount of the substance present at any time t, okay, assuming that x is the rate of change is directly proportional to x, after 15 years 30% has disappeared, and since x always denote the present amount, no, so x is 0.7 times x sub o. So if 30% has disappeared, 70% remains in the, or 70% of x sub o is remaining. So from example 1, okay, dx over dt is equal to kt. So this is your differential equation, and then we only have the same solution. Okay, so at t equals 0, your c, the arbitrary constant, is the initial condition, the initial value, initial amount, and then after 15 years you can compute for k here. So x is 0.7 x sub o, and then x sub o e to the k multiplied by t is 15. So this will cancel out. So this will give you ln of 0.7 divided by 15, or your k is negative 0.0. So this is your k, negative 0.0237. Now the negative sign here indicates that, or indicates a decrease, no, in the amount of x. And this is your x as a function of time. So at any time t, you can, at any given time, okay, you can solve for x in terms of the original amount. And then at half-life, so we can use this. Okay, so using again this equation, your x will be 0.5 x sub o, and then this is your c, e to the k, this is your k multiplied by t. So this will cancel out, and obviously you can again compute for t, and time, the time here represents the half-life, no, so that will be 29.15 years, which represents 50%. 50% of the original amount has disappeared. Okay. The second application is a Newton's law of cooling or heating. It states that the rate at which the temperature of a body decreases or increases is proportional to the difference between the temperature of the body and the temperature of the medium. So if T denotes the temperature of the body at any time T, Tm is the temperature of the medium, K is the proportionality constant, then your rate equation will be D capital letter T over D small letter t equals K times T minus T sub M. Okay, so if K is positive, your proportionality constant is positive, denotes heating, and then you will get a negative value of K if the problem is cooling. Let's take this example. If a thermometer is 75 degrees, is exposed to a room temperature, to a room where the temperature is 35 and the thermometer reading is 65 degrees after 30 seconds or 0.5 minute, how long after the exposure will the reading be 50 degrees? What will be the thermometer reading 3 minutes after the exposure? Okay, so T denotes the temperature of the thermometer at any time T. Our constant temperature will be 35 degrees, no? So that will be the temperature of the room. So this remains constant at any time T, which is 35. That will always be your medium temperature, no? And then using the Newton's law, the differential equation, no, for the Newton's law of cooling, this will be your equation, and then that is variable separable. Okay, so cross multiply your T minus 35 here and then integrate both sides, no? Integral of this will be ln of T minus 35 KT plus constant, and then solving for T minus 35 here. Okay, will give you e to the KT times e to the C, no? KT plus C can split, but this is just equal to C, and then transpose is 35 here, no? So that will be plus 35 here, Tm. And then at the initial condition, the temperature is 75, so substitute here C e to the 0 plus your 35 here will give you the value of C. So you will observe that the arbitrary constant is always obtained from the initial condition for first order, and then after 30 seconds the temperature becomes 65 or equivalent to 0.5 minute. Okay, so substitute here in this equation, the temperature is 65, your C is 40, so e to the k 0.5, that's the time, and then the medium, the temperature of the medium. So the second condition will always solve for the proportionality constant, no? And that gives you negative 0.5754. So this is a cooling problem. And then your T as a function of time will be this one, this equation. And at any time T, you can compute for T, the temperature T. Or given the temperature T, you can compute for the time. So we're asked to find the time, no, when the temperature is 50, so substitute here. and that gives you 1.7 minutes. And then at time equals 3 minutes, at time t equals 3 minutes, so what is the temperature? So again, substitute here, the time is 3. Okay, you can compute for the temperature, which is 42.12 degrees.